with effects that I use it yet a different way. I use it in the same graphical function, but I only take into account the positive half and I use it as a power transfer curve. Okay, this is a voltage transfer curve, it's instantaneous. Power transfer curve assumes that you're doing some averaging and you're looking at power. And we'll see that that's useful for the compressor and how we analyze and summarize how a compressor or expander or noise gate works. Okay, so this is class A, and that's actually without saturation. I'm driving it right to the edge of saturation. If I went further, the top to bottom would be clear. All right, so that's class A. What's class B? Well, class B is, again, I think I mentioned that each device is conducting less than 50%. So obviously, there has to be multiple devices, otherwise you could only amplify half the waveform. So we have the two devices. So we create, we have the same thing we saw before in class A. We have the signal generator, the slider gain, the bias. And then we have the saturation, if you see. But we also have the dead zone, right? And what does the dead zone represent? With the transistor, right, you've got the dBe voltage before turn on, right? So you got what it's for silicon, it's normally about 0.7 volts. Germanium transistors are low. And again, germanium transistors are common, or were common, and are brought back in a retro thing in music electronics because they have different tonal characteristics. And they have a lower dBe. I think you can get down to 0.4 or less than 0.2. Yeah, so, and again, all these depend slightly on the transistor. So VBE is what gives you the dead zone. Similarly with tubes, you can have turn on voltage indicate to cathode, and MOSFETs, you have your VGS, gate to source voltage. Okay, so here a conceptual block now. These two things are representing a transistor, and these are representing a transistor. And actually, the way I have it, you can't quite see it here, but the way I have defined this dead zone is that one of them, has the 0.7 and then does the negative, and then the dead zone continues out, so that this transistor only amplifies the negative going part. And then the other one has a transfer function that is only the positive going side. Okay, so you can't, unfortunately, the Simulink diagrams don't update to show that. So they're just icons. Okay, so in the class B, everything's operating half the time. We want to bias it excuse me, such that each device conducts during half of the cycle. The top is usually positive, the bottom is doing the negative. Now the benefit of this is that at quiescent point, at zero signal, nothing is being dissipated because both devices are off, right? That you're within this dead zone, you're within that dead zone, no quiescent current. So you've automatically, you've increased your efficiency. And typically what they do too is they pair the devices. So when you pick the transistors, you get a matched pair. You buy them as a matched pair. When you do the tubes, you buy matched pairs. And the way they match them typically, they build them all and then they test them and line up the two sets. There are whole companies that for tubes are based on this principle. There's a company called Groove Tubes. And what they do is they buy, I think they make some of their own tubes now, but they buy other people's tubes. And then they match them up. Not only do they match them up so that they say, here, this works together. They match them up and they test the gain. And they say, okay, here's a set that works and it's low gain versus here's a set that works and it's high gain. So depending on what you're looking at, you can buy something from 1 to 10. Okay, so that's class A class B. So we look at class B and we look at the output from the top. It looks like the incorrectly biased class A, right? It's amplifying only the top half. We look at the output from the bottom, and it's the mirror image of that. It's amplifying only the bottom. All right, so we put them together to try and get something that represents the sine wave we put in. And what's the problem?
We both go through cutoff at the same time.
Right. They both have the crossover distortion. So this is, now again, we talk about distortion and saturation and the musical aspects of that and the high gain amplifier. Now, a lot of people like, I mean, what is rock music without distortion, right? It's not crossover distortion. It's saturation. Crossover distortion doesn't sound very good. There are actually some devices that do something akin to crossover distortion. There's a pedal called the Machine, and it does something but crossover distortion, although I've heard it does some extra stuff. But if you read the description of the Machine, it explicitly says that, you know, other devices distort at the peaks, and we distort in the middle. That sounds like crossover distortion. It sounds like a definition of crossover distortion. But I've been told there's some other stuff going on. Unfortunately, I didn't analyze it when I briefly had one in my hands. So that is that's class AB, or excuse me, class B. So in order to try and get away from this, because that's unmusical and not pretty sounding, we get, okay, this shows the graphical transfer function. So that's the same thing we see. The fix for class B is class 80. All right, and the idea here is that we give everything a little bit of a lift just to get it out of the region. So here, when we split our signals, you know, and this thing here is representative of a phase splitter, right? A phase splitter says it takes your input and creates an in-phase signal and it creates an out-of-phase signal. Because you only have one power supply right now. So even though we talk about the positive side and negative side, you know, we have to create the two signals for amplification. So you need to basically invert it to get that other side. So that's what, it's not shown here, but that's what this represents. So what we do is we increase the bias to get it over to the dead zone, so 50.7. And then we decrease the bias on the negative going side. So I subtract, you know, 0.7 times 2, 1.4. So in this case, each of the devices is conducting a little bit more than 50% of the time, but less than 100%. And the idea is that we conduct during half of the cycle, plus a little more. Class A, B are more efficient in Class A, but not efficient in Class B, because you still have some quiescent current, right? The problem with this model is that I'm showing a very hard, rigid dead zone, whereas obviously, you know, a transistor is more, has that exponential. So, you know, before you get to this point, you get a little bit of turn on. So there's a little bit of quiescent current. It's not as bad. But again, each of the devices are conducting half as much. And these are more common in the larger amplifiers because they're more efficient. Because you can run things high. So your louder Fenders and Marshalls and stuff are Class A. And then actually there's an interesting thing with tube amps that they have a distinction. They have Class AB1 and Class AB2. And that's determined by whether grid current flows.
What's grid current?
We'll see that when we get to tubes. We'll talk about grid. Basically, the way to think about it is that a tube behaves similar to a MOSFET, or similar to a FET. Okay. With a MOSFET, it's impossible to get gate current, right? Because it's insulated. But with a BJT or a JFET, it's possible to get the current. And you've got, you know, with JFETs, you got leakage current versus biasing things correctly, make sure you get things right. With tubes, you're kind of isolated, and depending on how you drive the bias, you shouldn't get current. But it's possible to get current. It's possible to get electrons to flow in the grid. And we'll take a look at that. Okay, so Class A, B outputs. You know, these kind of look similar to Class B. If you look at it very, very